Okay guys, today we're going to be working on example problem 10.9, and this problem has to do with thermal energy. All right. So thermal energy is basically the sum of all the movement of molecules. All right, if you have a hot drink like coffee, its molecules, the water molecules in that coffee and whatever else is in there is going to be moving around a lot faster, a lot more vigorously than something that is ice cold. And so there's a way we quantify thermal energy in physics, and a lot of it has to do with friction. So if you've ever been out on a cold day or your hands are numb in the winter, you kind of rub them together really vigorously and that generates heat, right? So we're going to take a look at the math behind how that heat is generated, right? So the example reads that a 0.30 kilogram block of wood is rubbed back and forth against a wood table 30 times in each direction. The block is moved 8 centimeters during each stroke and pressed against the table with a force of 22 newtons. How much thermal energy is created in this process? So, a lot going on there. First thing we need to do is to write down our givens, right? We are given the mass of the block, so we'll write down mass is equal to 0.30 kilograms. All right. Second thing is that the block is rubbed against the table 30 times. So this is going to be for distance. So it's 30 times in each direction. So that's 30 times 1, 2, 3. All right, so it's going to be times 2. Whatever the displacement is, it's moving over 1 and then back 2. And then we're going to go 8 centimeters each stroke, which is going to translate into 0.08 meters. Okay, this is important because that 0.08 meters is going to give you the correct answer. Otherwise, you're going to be off by 2 orders of magnitude. So whenever we're working with these formulas, almost always, 99% of the time, you're going to want to use meters. Right, so, and we are looking for the thermal energy created in this process. Okay, so we'll do ETH is unknown. All right, so we have our givens over here. That looks good. Let's start compiling what we need to work with formula-wise. All right, so our formulas. In this section, we just covered that the change in thermal energy, ETH, is going to be equal to the force of kinetic friction times the displacement. Change in x. So that's all well and good, but we don't know what the force of friction is, and we're not given a force of friction. We're given a displacement, we're given a mass, but we don't know what the force of friction is, so how can we find that? Well, going back a little earlier in previous chapters, we know that the force of friction, kinetic friction, is equal to the coefficient of kinetic friction, all right, and that's mu sub k, times the normal force, right? So the coefficient of kinetic friction multiplied by the normal force is going to get us the force of kinetic friction that we need for our formula, right? So our key here is how do we figure out the normal force? Well, let's think about this example. We have our object, right? We have our block of wood or whatever it is that we're rubbing across the surface. What forces are acting on that block of wood? We have the weight, all right? And we have the force that we're exerting on it from pressing. In addition to that, we also have the normal force that is counteracting both of these forces because the block's not going through the table. All right, the table supports it even with the added force and the weight. So we know that the normal force, or F net, is 0. Okay. Now, what do we do with all this information? We're going to want to put it into its own equation and see if we can isolate normal force. Okay? So if it's in its own equation, we can kind of work with it by itself and see if we can get what we need, which is N. All right, so let's see. So the sum of all the forces in the Y is going to equal, all right, N is a positive force. It's pointing up, positive Y direction. So N. W and F are both negative forces. They're pointing down, minus W minus F. And we know that all of these balance each other out perfectly, all right? So they're equal to 0. Okay, now let's make an equation with that. Let's add W and add F to both sides of the equation. All right, this is going to cancel these out on this side of the equation and leave N by itself, which is what we want. N is equal to weight plus force. All right, and that makes sense because N is working in the opposite direction of weight and force. So if we add them together, they have to be equal. All right, the normal force has to equal both of these together. Otherwise, the sponge would be flying off the table or going through the table, and that's not what's happening. Okay, so we have the normal force. Well, that's good because that's going to give us our friction force. Now we're looking for this mu sub k. Now, with this, you'll either have to look it up or it'll be given to you. In this case, we had to look it up, and it comes out to 0.2. So we're going to put that in our givens section. Mu sub k is equal to 0.20. And because it's a coefficient, there's no units associated with it. All right. So now we're ready to solve. All right. Let's go ahead and plug in our coefficient of friction, or not our coefficient, our force of friction into our thermal energy formula. If we do that, delta ETH, I'll write that as a subscript, erase that, ETH is equal to mu sub k times the normal force, all right, because we're subbing this in, times the change in distance, right, or change in x. Now, remember, if we look over here at our distance, we got a lot going on, 30 times 2 times 0.08 meters. So we're going to have to implement that all into our final equation. Let's go ahead and write that all out. So delta ETH is going to equal our coefficient of kinetic friction, 0.20, times our normal force. So that's going to be, our normal force is going to be equal to the weight plus friction. Really quickly, weight is going to be equal to the mass times the force of gravity. All right, we've done this before. So our weight is 0.30 kilograms times gravity. We know gravity as 9.8 meters per second squared. All right, that is going to be added to the force put down on the block, which we did not write down in our givens. So that force is going to be equal to 22 newtons. All right. That's given to us in the problem, so sorry for not writing that down ahead of time, 22 newtons. Okay, and that's all for our normal force. Now we have the added in distance. That's going to be equal to 30 times 2. So we're going to multiply that 30 times 2 times, and then underneath here, 0.08 meters. Okay, so a lot of math going on. All right, and we're going to work on it step by step. Okay, so go ahead and get our calculator out, and let's kind of break this down. All right, so let's solve for the normal force here. So we have 0.30 times 9.8 plus 22. So all that together is going to give us 25 newtons. Right? Cool. So that's helpful. Now let's look at our total displacement, our total change in x. We have 30 times 2 times 0.08 meters. That's going to give us 4.8 meters total displacement. Right, so again, very useful. And then down here we have our coefficient of friction and nothing to multiply that out by. All right, lastly, we multiply this all together, and that should give us 0.2 times 25 times 4.8 equals 24. And newtons times meters is Newton meters, which is equal to 24 joules. Newton meters is the same thing as joules. So our total thermal energy generated by rubbing this block back and forth is going to be 24 joules. All right, so that should be your answer. That is the correct significant figures, and this should be your process. So on your homework, write out your givens, write out your formulas, a free body diagram if you need it, any of this that helps you solve the problem. All right, so go ahead and give that homework a shot, and as always, feel free to email me or ask me if you have any more questions or need any help clarifying some of this up. See you in the next video.